Thank you. Good morning, good afternoon, everybody. I am very pleased to host this fourth episode of our WPT Initiative Vodcast with Professor Seung Yang Han. He received the BS and MS and PhD degrees from the Korea Advanced Institute of Science and Technologies, KAIST, Daejeon, South Korea in 1998, 2000, and 2005, respectively, in electrical engineering. From 2005 to 2009, he was a senior engineer with Samsung Electronics, Suwon, South Korea, where he was in charge of high-speed board design for laptop computer systems. He's currently a professor with the CCS Graduate School of Mobility, KAIST, Daejeon. He has been working in the area of wireless power transfer system, electromagnetic compatibility design for electric vehicle, and high-performance digital systems, publishing more than 300 international conference and journal papers. He was the distinguished lecturer of IEEE EMC Society and the recipient of several awards, including Technical Achievement Award in 2024 and Motoisa Kanda Award 2021 in IEEE EMC Society. Thank you, Professor, again for accepting our invitation that will for sure be very much inspiring for our students and colleagues.
Hey, thank you very much for the introduction, Alessandra. So it was very nice to be here and join this Vodcast program. Yeah, thank you very much for this chance.
Thank you. So first of all, let us start with a general overview of the status of wireless charging electric vehicles that are development at KAIST.
Yeah, okay, I'd like to show some slides. And
please.
Okay, so nowadays we have before starting, I'd like to mention that respected Professor Kovic, in the last episode, he introduced the history of the IPT for electric vehicles. So some contents could be overlap. So I'd like to focus on more issues on EMC or EMF issues for wireless charging. So nowadays we have many kinds of applications for wireless power transfer. Basically, there's a long history of microwave power transmission, like solar power satellite, or some very short distance wireless power transfer. The magnetic resonant wireless power transfer technologies are popularly used. And nowadays we all have smartphones, and most of them are wireless charging. And now it's time to use these wireless power transport technologies to electric vehicles. So, and another example like biomedical devices or sensors or IC and packages, and they are also trying to use it, but it will take some time. So I'd like to more focus on the electric vehicles. And nowadays, wireless charging markets are increasing, and currently, more precisely, mass production of electric vehicle wireless charging not started yet. So, but still, there are a lot of researches on electric vehicle and robots and drones, especially for transportation systems. So it is, the market revenues are increasing fast. They are, maybe all of you already know that. So I'd like to skip some of slides which were related to the history. So yeah, Nikola Tesla stories and some one of the history of that actually, which was not well detailed introduced in previous episode. Actually, when we started in KAIST on the wireless charging electric vehicle, this PATH project was one of important reference. This, as you can see, the number is not very small, but this is a report of 1992. So in this report, they tried to make while charging electric vehicle. Actually, this past project, which was done in 1980s, was a big project related with general transportation systems, but some part was related while charging. According to this report, they used 400 hertz of frequency to charge while charging electric vehicles, but this report says some problems of that experiment. So yeah, it was long time ago, and some electronic devices was not so improved, which means that at higher frequency, like some tens of kilohertz, very high efficiency semiconductor devices was not developed yet. So they had no other chance to use higher than several hundred hertz. So the efficiency was very low, and the power line requires very high current in the transmitter, and it induces very strong electromagnetic field and some audible noise. There are many problems were reported in this work. So after that, we also checked what was the problem and how we can solve this problem. And also in 2009, we started our new project, but also this work was also one of the big reference, which was well known to everyone, the MIT science paper published in 2006. In this work, they showed how they efficiently used the resonances to enhance the distance. So in this paper, the power is transmitted to 2 meters of the distance with the efficiency of 40%. Actually, this is coil to coil, not including the conversion efficiency. Anyway, this was encouraging us. We can have a more higher efficiencies for even higher power systems. So previously, yeah, some of part already introduced in previous episode, but Vampro and Showa in Japan, and there are previous researches, including Kovic's work, and there are example of transportation for wire charging. So what we focused on was to emphasize to increase the air gap. So at the time, the air gap was very small, like 10 centimeters, which means that in actual road on the highway or in the metropolitan area, it is very difficult to drive the car with just 10 centimeters air gap. It's speed bumps can damage the car, something like that. So what we focused was, of course, the power is increased. The target power is 100 kilowatt, but important thing was air gap of 20 centimeters, and which means that the transmitter and receiver must be around 30 to 35 centimeters of distance, because it includes some case or something like that. So the what we have done was to supply the power with 20 kilohertz, and this current is going into the current wire on the road. So this is generating magnetic field, and the magnetic field was captured by the pickup module in at the bottom of the vehicle. So this dynamic and stationary while charging was interesting. So at the time, many people didn't believe that this could be possible. So, but anyway, after some time, we have proved that this is possible, and we constructed several sites for test projects, and now we are facing several problems. So here we fundamental technologies are all developed. So power can be transferred, and the air gap was enough to charge the vehicle, and this technology could be possible. And many industries like car manufacturers are interested in. Recently, Tesla also had a presentation that they would like to use the wireless power transport technology for robot taxi, autonomous driving taxi. So, and also in Korea, too, Hyundai Motors are trying to adopt the wireless charging technologies to Genesis GV60 model of electric vehicle. But actually we face some problems which was not actually seriously dealt before. There are, for me, yeah, just to summarize it, we have just two big problems. One is the cost. Yeah, the technology is very good, and we can charge the vehicle every time on the road, on parking lot, and everywhere. But to make it commercialized, then we have to make it cheaper so that the people can buy. The convenience and the cost should be compared. So as the market is always very strict. So if, even though very good technology is applied, if it is too expensive, we cannot buy that. So actually the biggest problem is the cost. And in technologies, we have to make some more technology to make it cheaper. And another one, I think, is the problem of electromagnetic field. So now any electronic devices on market, we have to get the certification of EMC and electromagnetic safety for the human body or something like that. That kind of problem is still not solved yet. So currently, yeah, basically the wireless power transfer fundamentals are, yeah, generating current in the transmitter, and magnetic field is generated, and the receivers get the power from the magnetic field. But here we can see that the proper frequency. So a long time ago, it was 400 hertz or 20 kilohertz, or nowadays we are using 85 kilohertz more. But if we increase the frequency, basically the magnetic coupling increases and efficiency generally increases. But there are switching losses and some radiation and some other issues happens too. So when we increase the, I'm sorry, I'll try to skip some of slides. So here, when we are using some tens of kilohertz of frequency for while charging electric vehicle, the frequency is not as high as gigahertz, then the field is not going this way. Always the low frequency of the kilohertz of range is going outside. It goes everywhere. So what we have to consider is that this kind of leakage magnetic field must be considered and controlled. Still, when power of the electric vehicle is increasing day by day, for example, yeah, the early version of this electric vehicle about 10 years ago, the battery was 20 kilowatt hour, which can drive around 100 kilometers. But nowadays the size of battery is increased, and now we have more than 100 kilowatt hour of large batteries to charge it, which means that if we charge it, the standard 10 kilowatt or 11 kilowatts of chargers of wireless charger, we have to charge it more than 10 hours. And people want to reduce the time. So we have to increase the charging power. So original one was 3.7 kilowatt and 7.7. Nowadays 11 kilowatt is the standard defined in the SAE J2954. So and the next version of the wireless power with the 22 kilowatt is now in TBD, and they are trying to make a new version of that. So in this
So
increasing power, yeah, sure, you
yes,
can.
just to focus on these points, very interesting and very detailed. Do you think that the most issues to be overcome for effective commercialization of wireless charging for electric vehicle are both the cost of the entire operation and the time needed to charge the batteries? So which are the main technology challenges to solve these problems, in your opinion? For example, in terms of new devices, and also, since I am a wireless power transfer expert in high frequency, do you think that increasing the frequency, further increasing the frequency, will meet this goal while keeping EMI and EMC under control?
Yeah, to solve that problem of the cost and EMC, on the frequency, actually, it is very difficult to change the frequency so different from current frequency range, because they are all standard, and if we increase the frequency too much higher, then the device switching loss would be much increased. So that conversion efficiency must be guaranteed. So I think the frequency would be 85 kilohertz or around that, not that much. And also to solve that, the some development of the new devices or switching devices could be helpful. But no, the efficiency currently is dealing with a change of just a few percent. So not that much of a power, the efficiency could be expected, even very new devices or something like that. So currently, for technically, yeah, the wireless power transfer itself, the very difficult problems are already almost established. So now it's time for development from the industry to make it cheaper and compact and more comfortable, and additional some functions they are needed. And for me, yeah, I'm working on EMC. EMC problems are still very difficult to solve because power is increasing, and this is wireless, not the wired. So we cannot add some additional shields, something like that. So especially for the vehicle, it was very difficult to add something because already there are many parts in the vehicle. We cannot remove all of them. So with the structure of the vehicle, it is very more practical researches, including the current situation of the vehicle structure and adapting the shield technologies to the vehicle. That kind of part is also needed. In addition to that, we are now changing some materials so that current limitation of the materials of the magnetic material, ferrite or something, to make it lighter or cheaper or smaller. Yeah, some additional practical technology could be applied.
Okay. Thank you. And concerning railway, what is the status of WPT for railway application?
Yeah,
in Korea,
so
in particular. In Korea in particular. I know that there are some research projects running for some years, and so it is interesting if you can comment on the status of this project, because in that case, the challenges that we have considered are more and more significant.
Yeah, the railway system is very cost-effective transportation with less it's good to the environment and energy efficiency. So yeah, in many countries, including Korea, trying to use the wires power for railway systems. So the remover of the overhead power lines and this kind of pole and all wires and pantograph and this kind of catenary cable, they are all big burden for railway engineering. And there are in Korea also we have a lot of accidents in maintenance. Engineer they have some trouble and by mistake, or some general public also have some trouble with the high power current of the railway system. So so some railway companies like Bombardier or some many companies, railway companies try to apply this. In Korea, actually, after we finished the first phase of wires power transfer for electric vehicle around 2015, after that we started a new project of railway system, because the railway system has a much less trouble than the electric vehicle system, because the train is always on the rail, iron rail, and the wheel is iron. So we have very small possibility of moving laterally or vertically. So because of this, and also the rail is always on the rail, so we can reduce the air gap. In case of vehicle, we have to make an air gap 20 centimeters, which means that more than 30 centimeters of coil to coil distance. But in our case, in this railway case, we can make it 10 centimeters or less. So depending on the speed. So the coupling between transmitter and receivers could be much higher, and as you know, the train is longer, so and we can make more receivers and long transmitters. In addition to that, generally train is the wheel of the train at the bottom of the train is generally has a longer distance from the passengers. We have the platform of the station, and electromagnetic field leakage could be also less problem. So yeah, so currently we first finished the test of the development of the railway system wires power a few years ago, and the next of the high speed power is being prepared. So the first one was the 200 kilowatt for the tram, and 1 megawatt for high power system, high speed trains. So they are trained. The
1
test site
megawatt.
is constructed.
Wow.
Sorry.
1 megawatt for the high speed train.
Yeah, 1 megawatt.
No, the
Yeah.
highest. Okay.
But actually the train is longer, so it's we have a lot of modules connections.
So we can conclude that although we need such amount of power, perhaps designing a WPT system for railway application will have less degrees of freedom, so less unknowns than the case of electric vehicles. So you have already an interesting prototype.
Yeah.
Okay.
Okay. So this is example, and I'd like to add some more applications, something like that.
Yes.
This underwater system. Yeah, the underwater. Yeah, this is one of the big project going on in Korea. So, yeah, underwater always we have a problem, yeah, the for the power supply. So some this kind of unmanned underwater vehicle can be moving by using the electricity, but always we have to bring it out to the ship and replace battery and go down. And also because of the salty and then humidity makes the any kind of the contact will be not working properly. So this kind of wireless charging system is very useful in underwater system. So some in the underwater charging station can be also possible, and some analysis on the power transfer in conductive medium is also studied like this.
What is your opinion in this case? Yes, I agree with you. Underwater wireless power transfer for underwater application is a very timely research field. And there are many researchers that are addressing capacitive links instead of inductive links. So what is your opinion in this respect? Do you think they can both obtain the same performance, or perhaps one of the two is still the winner?
Yeah, the capacitive coupling is also one of the solution to power by using electric field. But in many cases, the wireless power with the magnetic field is more advantageous in several cases, because the just like in this underwater system, for example, the water is conductive, especially in seawater. We have some conductances, so it can generate some eddy current inside the conductive media. So
Yes.
they can be even more possibility that we have to consider any leakage current. But in case of magnetic field, there could be some eddy current, but below the 100 kilohertz, or maybe in our experiment up to several hundred kilohertz of range, this eddy current could be ignorable. But in case of by using electric field, they are more affected by the dielectric constant, the loss and the permittivities. So in case of magnetic field, they are generally affected by the permeability, which is generally 1.0
Yes.
value. So they are less affected. So that's why one of the reasons. Yeah.
Yes, so you think that the advantage of having a higher permittivity is not cannot be exploited because of losses. So so on the overall, the budget is in favor of magnetic resonant fields techniques, even underwater.
Yeah, even on the water, and in many applications, it's more advantageous. But still, the capacitive coupling can be also advantageous in some applications.
Which are the applications you see
Uh,
that can exploit successfully capacitive, so electric field coupling?
yes. So I'd like to skip a few slides. I'm sorry. So
And then we
this
can
is
go back.
this is one example of the CPT application
Yes.
for drone.
Mhm.
So the reason why we started this was that uh, you can use the capacitive coupling without ferrite material, magnetic material. The reason why magnetic material is more effective is that we use magnetic material which is very heavy. So in case of the air gap is not that important, and some we can design some structure like this. I'd like to show the results actually. So this is one of the example where the drone is landed, And at the bottom, we have a circular metallic plate, and the orange color and lighter and darker orange colors are RX and TX and RX. So we have two capacitors for capacity power transfer. So in case of IPT, we can place the coil here, but to enhance the efficiency, we have to add the ferrite. So because of the ferrite, of course, efficiency is a little bit higher, but the 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 weight
Wait.
of the TX and RX are heavier, especially RX side is
Yes.
higher. Yeah, so that's one of the issues. So in some cases, so we can use CPT rather than IPT.
Very interesting. Yes. Yes, this is a very interesting aspect. In drones, of course, if you increase the weight, you increase the power needed by the drones to fly. So this is a very interesting. And you have some demonstration. Are you planning to commercialize this CPT system for drones?
But actually, yeah, the commercialization must be related with some industries, but not yet. That the market of the general drone makers are not much interested in this product because recently the Amazon was still working on that, but still the
It's still
market
at
is not
the
open yet.
research level.
Yeah,
Okay.
that's
Then,
why.
uh, what are other applications that are very promising that exploits this kind of technology, and also they are more, in my opinion, sensible to the effect, the electromagnetic effect. I am talking about biomedical devices. Can you please comment on your activity in that field and expand my principle about the aspect related to EMI and EMC?
Yeah, that's a really good important point, and I'd like to just a moment. Yeah, so there are many applications like a biomedical devices, and now the medical devices are more electronized and they are intelligently working inside the body. Some stimulators and sensors and monitoring systems are popularly used. And by using the wire's power, we can charge the devices implanted inside the body wirelessly. So we can, if we use just lithium battery, for example, then without just one-time battery, is that we have to replace it by the surgery to just like implanting the devices inside the body. So when we charge the device wirelessly, then we can extend the surgery period more than several years so that the patient could be more happier. So this implantable biomedical devices could be one of the possible example. Then this is kind of example of cardiac sensors, which detects the heart beating of the human. So this is the of a few centimeters of size. Actually, this is a test. We made it bigger. So anyway, here we have electrodes which detect the sensing of the very small electronic signals when the heart is beating. So we had a test on a rat, and we have a showing the example of the test. So the communication between the implanted sensors and the device is the system is communicating by using 6.7 megahertz of frequency with the communication, and only when we charge it, we place the charger closer to the device, and for 10 minutes or 1 hour, and then we use it for some hours or some days. So in this way, the implantable devices can be used, and we have to also consider the heating and electromagnetic field. So the heating is also important because some part of our body is very sensitive to the temperature. So we have to make an efficient device to make less heating from the device, and also the electromagnetic field as the device is inside the body, even the charging electromagnetic field is still inside the body. So the heat problems and EMF, electromagnetic field problem, must be considered carefully in case of biomedical devices.
And
So,
also,
yeah.
if I understand correctly, you have combined in that application both transfer of energy and of information using the same link. So you exploit both technology. This is very interesting also. Yes, but I think this is the field where EMF is more important and a real issue. So please.
Yeah, right. So so in case of the EMI issues, we have to actually the EMC is also one of the research field with a long history. So there are many issues and susceptibility, ESD, and signal and power integrity pulse or radio frequency interference. But in case of wireless power, we have to focus on the two issues: the electromagnetic field (EMF). Generally, we mention EMF word as the effect on the human body, and the EMI is the general interference to other electronic devices. There's actually similar, but some differences, because EMF is more sensitive to the magnitude of field. So the more fundamental multiple harmonics of the fundamental frequency is generated also in wireless power. But in case of EMF, strong magnetic field would be fundamental frequency, and it would be the lowest frequency. So we are generally consider the fundamental frequency in near field. In case of EMI, some very sensitive device can be interfered by even small electromagnetic field if the frequency is exactly the same. So we have to consider multiple frequencies with a harmonic, and we have to consider the sensitivity of other electronic devices. So here,
just a moment. I have a question just for the audience.
Yeah.
Can you go back to the previous slide? Which are the other aspects less relevant? You talked about radio frequency interference, and the other ones, just to let people know.
Yeah, radio frequency interference, or generally it's inside intra interference or signal and power integrity or something like that. They are also required, but in case of low frequency, like some kilohertz of range, the signal and power integrities or some that kind of issues are not that important in case of the but for micro power transmission, which uses several gigahertz, they can be also serious in signal and power integrity issues. And the EMP or RFI, they are yes, depending on the application, we have to consider that. But the biggest problem is the EMF EMI. So
do you think ESD, for example, is electrostatic discharge? Is it a problem in WPT systems, for example, for application in biomedical implantable devices or not? Or
in case of ESD, there are several solutions to protect it, but for ESD area, actually, this is not my the major, but we have to concern that, especially for high power, actually, very high power system. If we are dealing with, then on the surface, there should be some currents, and we have to some electric unaffected discharge can be happening, and also the solution. But in this ESC are generally mentioning that sensitive transistor parts should be protected. That is some other issue, but depending on the situation, depending on the application, sometimes we have to concern that. Yeah.
Thank you.
Yeah, right. So in case of the EMF NMI, so yeah, near field and human and also multiple harmonics
Yeah.
Considered. So
And can you comment on the levels of the higher harmonics with respect to the very high fundamental? Because in my opinion, the fundamental harmonic is under control due to the entire system. What happens to the higher harmonics up to the seventh or higher level? Since they can be very low for the wireless power system, but can be significant, for example, for communication. So these are, in your opinion, the main source for EMI?
Yeah. Actually, the frequency is some tens of kilohertz of frequency, but we had some experiment that when we use even 20 kilohertz of frequency for the charging of the electric bus, but we had some experience of some megahertz of megahertz or 100 kilohertz of range, which is that several 20 or 40 the harmonics of the frequency. The radio AM radio was interfered, and even is 50 times higher than the fundamental frequency. But if the frequency exactly match, then the noise could be affecting the system. So it's very high, very wide range of the frequencies considered.
Yes. Thank you.
So yeah.
Yes. So now I think the audience is very much interested in the possible issues for the bodies and if they affect in some way, or obvious, as I expect in your research, you have already thought about all the solutions to protect
There are,
in the case of the driver, for example.
Right. We have some minutes. So this is an example where the electronic field can treat the brain cancer, for example. So this kind of device actually means that indirectly showing that the field is affecting the body. So the WHO and IARC classify the electromagnetic field as possibly affecting the generation of cancer, something like that. So people are concerning that is very important. Actually, to affect the human body from the electromagnetic field, it takes a long time, and very strong electromagnetic field can affect. But in normal life, the electromagnetic field is not affecting seriously. But important thing is that people are concerning. So that's why the industries are trying to make us safer. So to solve the electric EMF problem, EMI problems, it depends on the country. So some countries have a very high regulation limit. So the design is very easier to for some countries, but for some countries the regulation is very severe. So we have to satisfy very difficult regulations. So to solve that, we have several ways, but we can consider which part we are trying to reduce the field by in the TX side or coil itself or at receiver side. In another point of view, we can use different methods like circuit design or shielding can be added, or balancing of the field can it's self-cancellation and make a smaller problem. So by using three-phase, in case of some researches in dynamic or stationary charging, we can have some aligning all the transmitters with a three-phase or single phase, and self-cancellation can make radiation from these coils. So for example, for EMI, for higher frequency, we can use the general simple inverter and make the square wave. It generates very strong electromagnetic field at higher multiple frequencies. But by using multi-stage inverters, which can make the step pulse, which seems like a sinusoidal wave, it can significantly reduce several odd number harmonics, and it can. This is also in the research. And yeah,
very interesting, because you are showing a reduction of 30 dB for the third harmonics and almost for the fifth harmonic.
This technology is also already used in some high volt DC or some power systems. So we are applying that technologies to wireless power system. So also balancing like that, the receiver coils other directions. One coil is having some current to this direction, and the other coil is the other direction. So at this side, strong magnetic field generation, but it's far from the measurement point. And this coil is generating opposite direction, but small magnitude, but it is near. So we can optimize the electromagnetic field at this point by controlling the number of turns and the size, something like that. So we can make a structure of the coil by cancellation and reduce electromagnetic field. So
you suggest, for example, a more distributed architecture of coils rather than large ones, because this can also be optimized for this goal of reducing EMF and EMI.
Yes, right, exactly. So the other application like polyphase or three-phase or something, they are all well distributed, and they are the opposite phase are canceling each other. So this a similar concept.
Very nice. Yes. Thank you.
And also we can use metallic shield or magnetic shield, but in case of wireless power, this kind of hardware shield is very difficult to use. So active cancellation or reactive cancellations are developed. The active cancellation is generating opposite direction of fields. So at this position, two fields are canceled out. Reactive shield is by using this magnetic field, this field excites this resonant coil, and the generated from this coil is canceling the original field. So this is also one of the promising technology. So in case of the application to the coil, we can apply the reactive shielding coil here or there. We just place 1 or 2 turns where the transmitter or receiver coils a number of turns, but we just have just 1 or 2 turns in addition outside. They are separated resonant coil. So because of the TX coil, for example, this TX coil red colors of magnetic field is exciting also the shield coil outside, and the shield coil outside, we can control the impedance of the shield coil by controlling the capacitor. So yeah, details are not, I don't have enough time to explain, but basically TX side, the power transfer coil is inducing the voltage at the shield. At that time, the 90 degree of phase shifted. And in addition, we have another shift of the 90 degree can make 180, then we can cancel each other. So the key is like that this is the main power transfer coil frequency. But if we set the shield coil frequency a little bit lower than that, then for the shield coil, this frequency's impedance is j omega L, which is positive. We generally call this is inductive region, and the left side is capacitive region. So if we set the resonance frequency positive imaginary, then this j plus j term is divided. So we can have additional 90 degrees. So original red colors magnetic field and generated blue colors of the magnetic field from the shield are canceling each other. So yeah, this is the kind of reactive shielding cancellation.
Yes, very interesting. These solutions, I think, will be very widely adopted, and I know it is already very popular, and it was your original idea. Do you think it does affect the overall efficiency of the system or marginally?
Yeah, of course, yes. Yeah, many times in EMC engineer, whenever we give a solution, always we have to pay. So the payment could be efficiency or size or weight or cost, everything. So in this case, we can, this is the example of the application of the shield in smartphone application. It reduces efficiency by 66%, even though the EMF was almost half. So we have to consider that the degradation of the efficiency. But when we design something and solve the EMF or EMC problem, always we are facing it can be certified or not. That in that problem, we can sometimes sacrifice the power transfer
Few
efficiency.
percentage of efficiency, but an extremely high reduction of the EMI problem or EMF problem.
Yeah, right. So I'd like to show there are some example like if we have some multiple frequency, because this was fundamental frequency reduction, but if we need third harmonic and fifth harmonic only, then we can use multiple resonances. In case of the single resonance, we reduce just one frequency. But if we use multiple resonance, like this circuit, which has two resonance frequencies, then we can have a first and third harmonic reduction. Or if we change the frequency, we can reduce the third and fifth, or third and eighth as the ninth or something like that. We can control it. Multiple frequency can be controlled. So actually the one of the last example to reduce EMI was that generally we have to pay the efficiency, but we are trying to increase the efficiency. So here, generally we want to increase the fundamental frequency, and for the harmonic, we have to reduce it. So from the idea that if the resonance in the left side, if the impedance of the shield is minus J term, then we have to we can even increase the field. So here we apply that idea that when the resonance frequency at this point of the shield resonance frequency is here, on the left side, the fundamental frequency is increased and the harmonic is decreased. So by using this, we can some increased. So here, this is the fundamental frequency here. The shield frequency is in the middle of the first and third. So this is the capacitive region, even enhance the field. On the right side, it decreased the field by the cancellation. So this is the example that the efficiency can be increased by 2.7%, and EMI is then decreased by 6.6 or 7 dB. Of course, we have to pay that we added some shield. That is the payment, but we can both increase the efficiency and decrease the EMI.
That's very interesting. Yes. So you think that as a conclusion, you can let's say ensure people that EMF and EMI may be mitigated at the expense of a small reduction of the overall efficiency and perhaps an increase of the system volumes and so on. But these solutions demonstrated that protection can be achieved.
Yeah. Actually, yeah, this is still before the mass production. Still, we are actually in the industry working on this wireless power. They are urgent because if the EMI and EMF problem is not cleared, it is difficult to get this product to the market. So, but fortunately, up to 10 kilowatt. Yeah, almost we have accomplished that. Actually, we satisfy the regulation in EMF and EMI, but the problem is the power is increasing, as I mentioned before. So I think applying this kind of technologies, ideally we can solve it, but the market will decide it, because to do that, if we have to add some many things and it increase the cost, and it is not cost effective, they are not welcome in the market. So I think that as a researcher, this kind of technology is already ready, but it's actual in the market, that this technology can be applied or not, I cannot be sure, but hopefully it could be possible. Maybe it takes some time, but the request for autonomous driving, wireless charging, and that request is higher and higher, and people understand the convenience, they will pay more, and we can finally solve all the problem with the reasonable cost.
And what about implantable device with respect to this? Do you think that exposure to EMF in this case is unavoidable?
Yeah, that could be possible, but yeah, I'd like to show some example that the difficulty of the biomedical application is more difficult, because yeah, even power transmission area, this field is also inside the body. So, but we can have some control of the EMF levels by using the cancellation. So basically, TX and RX are TX side and RX side in 90-degree phase difference. This is optimal and maximum power transmission. But if we sacrifice the efficiency, we can make TX side and RX side is close to almost 180 degree. So basically that the TX and RX has a 180 degree, perfectly 80 degrees is zero efficiency, but close to 80, like 170 or something like that, we can significantly reduce the electromagnetic field. But in case of the biomedical devices, fortunately, the efficiency is not that important because power consumption is smaller. So yeah, we have tried this application. So even yeah, this figure could be small, but between TX and RX, this is very light colors, but it came a little bit darker. So EMF was the 41%, and power transfer efficiency was also increased by adding some coils. So so that kind of technology could be also possible. Yeah.
Okay, so also for the body, since efficiency, as you said, is not the main goal, because we need power of the order of milliwatts or 1 watt
right.
at the highest level, we can work
Yes.
for protecting the human body. Thank you
Yeah,
very much.
right.
So, just to conclude our very interesting discussion about these issues that are strongly related to the exploitation and growth of this technology. How do you see wireless power evolution in the next years with respect to the other emerging technologies?
Yeah, so this technology was very highlighted in about 10 to 15 years ago, and just like the other emerging technologies, it it's experiencing very hard time. Some new technology was sometimes exaggerated, and after this about 10 years, now the good news is the industry is more interested in that, and they are actually paying money to the development and actual investments for the mass production. So I think the interest of the industry and researchers are again increasing, and I guess several years that we can see uh, the mass production of wireless charging electric vehicle on the road, on the market, and from beginning with less regulations, and maybe even though the power is increasing, maybe we have to develop some more technologies to mitigate the electromagnetic field, and yeah, I think the future is bright.
Thank you very much. Thank you, Professor Han, for this interesting conversation that has opened us, clarified a lot, in my opinion, the various aspects and interaction between achieving very good results in wireless power while protecting the overall environment. Thank you very much. And this
Thank you
concludes
very
our
much.
fourth episode. And I hope to see you in few weeks in Rome. As you know, we have the worldwide conference on wireless power transfer that is supported by IEEE. Thank you very much.
Okay, thank you. Thank you very much for your time and effort for this chance. Thank you.